Okay, so I had a few students that were asking for a few extra voltage drop problems to practice on before they took the exam. And so I put together a few of these. We'll work them together so you can look at the problem, pause it, work the problem on your own, and then you'll be able to hit play and see how we work it together. All right, so first one is what is the voltage drop of a 120 volt circuit with a load of 9 amps 75 feet away from the panel using 14 AUG copper wire? All right, so the first thing we have to determine, are we looking for the voltage drop or are we looking for the size of the wire? In this case, it tells us that we're looking for voltage drop, so we know we're going to be using this formula right here. So let's just start plugging numbers in. That's the beauty of having these formulas is all you got to do is if you have all the information, you just plug the information in. And so our voltage drop equals 2 times K. K is the average resistance of either copper or aluminum. In this case, it tells us that it's copper, so we're going to plug in 12.9 for K times I. I is our amperage. That is 9 amps. And D is our distance, which is 75 feet away. And then all of that is over circular mills. So we're going to find the circular mills of 14 AUG copper. 14 AUG is 4110. So we'll put in 4,110. Now we just have to do the math. 2 times 12.9 times 9 times 75 equals 17,415. Divide by 4,110. And we get 4.237. We'll round that up to 4.424 volts. Now, it didn't ask me here, but we're going to check anyways. What is the allowed voltage drop for 120 volts? The allowed voltage drop is 3%, so 120 times 0.03, we get 3.6 volts is our allowable voltage drop. So we're over our allowable voltage drop. All right, so that brings us to question number 2. Question number 2 is, what if we calculate the same load, we'll use 12 aught copper? All right, so if we use 12 aught copper, the only thing in our formula that changes is the size of the wire. Everything in the top half of the formula stays the same. But we're going to come over here to our chart, right? And this chart, remember, this chart is chapter 9, table 8 of the code book. I have a little excerpt of it here for working these problems. But you should be able to find that in your code book, and you should practice doing that if you have a code book. So number 12, circular mills, 6530. 6530. And so then we're going to multiply 2 times 12.9 times 9 times 75 to get 17,415. That should sound familiar because that's what we got the last time. And then we're going to divide it this time by 6,530 to get 2.67 volts. And so that's quite a big change from our last one. That puts us underneath the 3.6 volts that we are allowed. But it's a rather inefficient way to find what wire size we need. Like, we could plug in, all the different wire sizes until we found the one that was the closest to being within our range for voltage drop. But if we are looking to find the wire size that we need, it's much more efficient to rearrange this formula to look for the wire size, because we know what the voltage drop is, right? We know what the allowable voltage drop is, so we already have that parameter. We can plug that in to our formula, right? We could have plugged that in here. Well, we know that the allowable voltage drop for 120 volts was 3.6 volts. We could have put that in and found the exact wire size that we needed, and it would have came in between 14 and 12. We would have known that we needed to up that to size 12. All right, so in that vein, let's look at the next question, which asks us what size wire would be needed for a 120 volt circuit with an 8 amp load 50 feet from the panel. All right, well, it's asking what size wire, so we're going to use this formula. And we're going to circular mills equals 2 times K. All right, this doesn't tell us if it's copper or aluminum, so how do we know which one to choose? Well, if it doesn't tell us, we're going to assume it's copper. Aluminum is the outlier here, right? We are going to use copper because it's the best choice, unless someone tells us for some reason we need to use aluminum. There's a cost concern or something. We're going to use copper unless somebody tells us not to use copper. So if it doesn't tell us, we're going to assume that it's copper. So we're going to put in 12.9 times our amperage, which is 8 amps on this one, times our distance, which is 50 feet. And then all of that gets divided by our voltage drop, which for 120 volts is 3.6 volts. And now we just do the math, right? 2 times 12.9 times 8 times 50 equals 10,320. Divide that all by 3.6, and we get 2,866.67 circular mills. So then we just look over at our chart over here and see that that is bigger than a number 16, so that we're going to use a number 14 there, and we would use a number 14 for that problem. All right, so let's look at number 4 here. What size wire would be needed for an 11 amp 120 volt circuit 35 feet from the panel? Once again, it's asking for wire size, so we're going to use our circular mills formula. 2 times K. Our K is 12.9 because it doesn't say that it is aluminum, times our amperage, which is 11, times 35 feet. If you remember in class, we talked about in this formula, we have a wire going out to the device. We have a wire coming back that completes the circuit. So it's not 35 feet, it's twice of 35 feet, but that twice is already built into the formula. That's what that 2 stands for in the formula. It is doubling the distance. And so we put all of that over our allowable voltage drop, which is still 3.6. And then we do the math, right? These are not hard as long as we are able to find the right numbers to plug in. So 2 times 12.9 times 11 times 35 equals 9,935. Divide by 3.6. We get 2,759. Right? Once again, we're coming in more than 16, so we're going to be a number 14 wire. I should have picked some bigger numbers here, where we could have gotten into some bigger wires. But let's see what comes next here. What size wire would be needed for an 11 amp 240 volt circuit 65 feet from a panel? All right. So our looking for the size of wire, circular mills equals 2 times K, once again is 12.9, times our amperage, which is 11, times our distance, which is 65, all over 240 times 0.03 is 7.2 volts. Alright, once again, just doing the math. 2 times 12.9 times 11 times 65, we get 18,447. We're going to divide that by 7.2 and we get 25,062. So that's going to come in at a number 16, right? We're generally not going to use a 16. We're going to use at least a size 14 for anything that we do, but our voltage drop says that it has to be at least a 16. So if we use a 14, we're going to be okay. All right, let's see about get all that mess erased there, and then pull our chart down where we can see we can work some more problems here. There we go. All right. What size wire would be needed for voltage drop for a 3-phase load drawing 18.7 amps, 240 volts, 85 feet away from the panel? All right, so now we've got our first 3-phase load. We're using the same formula, but in our formula where our 2 is, we're going to change that 2 to the square root of 3. And the square root of 3 is if you could either put the square root of 3 into your calculator, or you can use 1.732. So we're going to substitute that in for the 2. Remember, the reason we do that is that 2 is representing in a normal circuit, you have a one wire servicing the load that goes out to the load, and one that comes back that completes the circuit. So it's 2 wires in that circuit. In a 3-phase load, there are actually 3 wires that are going out and servicing that load, but because it's 3-phase, those 3 phases interact with each other in such a way that we gain some ground on voltage drop, and so we can use the square root of 3, or 1.732, to calculate our voltage drop. Okay, so let's take a look at start plugging our stuff in, right? So we need to know our circular mills. It's equal to 1.732, or the square root of 3, times K, which we're going to assume is copper, times I, which is 18.7, times distance, which is 85 feet away. Let me move this over a little bit so we've got room. 85 feet away. And then all of that gets divided by our allowable voltage drop, which is 7.2 volts. All right, so 3 square root times 12.9 times 18.7 times 85, and you should have gotten close to 35,514.9. I use the actual square root of 3, so my number may be a little bit different if you use the rounded off 1.732. And then we're going to divide all of that by the 7.2 volts, and we're going to get 4,932.6. So if we look up here, that is bigger than a 14, so it's going to be a number 12 that we're going to have to use for the number 12 AUG is going to be our wire size there. All right, so now we look at last one we're going to do here, number 7. 3-phase 240 volt feeder for a sub panel with a 130 amp load 60 feet away would require at least what size wire? It's asking what size wire. And so if it's asking what size wire, we're going to use our circular Mills formula. Equals, it's not 2. We're 3-phase here, so it is the square root of 3, which is 1.732 times K 12.9 times our amperage, which is 130, times our distance, which is 60 feet, all over 240. It's going to be 7.2, not amps, 7.2 volts. Alright, so let's do the math. Square root of 3, or 1.732, times 12.9 times 130 times 60, 174,278 and some change. All that divided by 7.2 volts equals 24,205.4 circular Mills. Alright, so if we look up at our circular Mills, we're scrolling down 10,000, 16,000, 26,000. So it's bigger than a size 8. Size 8's not big enough. Size 6 AUG would be 26,240, and that's going to give us a large enough wire for that problem.